as we mentioned, we are going to discuss now the mapping process, so how you can basically move from a reference elements into any element. So first of all, let us just go quickly through the equations we have used in the past to develop stiffness matrix, and we will see how the difference or what differences will happen when we want to do this mapping process. So far we have used the shape functions, so it is n1 and n2. I'll probably just use red here. So it is n1 and n2 to interpolate the displacement at the node. So we have u1, u2, we do the shape functions, we interpolate them, we find the displacement anywhere inside this element. The strain displacement relationship can be found through the derivatives. And then we call the derivatives is just basically the derivative of the shape functions multiplied by u. These derivatives of the shape functions, so this one here, we call it the B matrix. We said this is a very famous matrix, so we give it a name. And then we take this B matrix, multiply it with the transpose of the B matrix, and we find the stiffness matrix. So these steps, they would remain the same. We are now going to find how to link it to this extra process. So I'm going to probably just start here. Now, first of all, we have the original element. Oops, I'll probably just use black again. So we had the original element to be of the length L. And then we have x1 to be 0 and x2 to be L. So this is what we had in the past. All right, so this is the x coordinate system, and it goes between 0 and L. Now we are going to forget about this for the time being. We are going to create a reference element here. So this is the reference element. It goes on some other coordinate system. We're going to create what we call a local coordinate system. This is going to be xi, and xi would vary between -1 to +1. Right? Xi is 0 at the center of this two-noded element, and it varies between -1 to +1. Now, how we are going to link x1 and x2 to xi1 and xi2, we're going to do this using exactly the same procedure we did for the displacement. So we're going to create a relation between the x and xi, and x is going to be n1, n2 multiplied by x1 and x2. All right, so we are going to interpolate the displacement exactly the same way. We are going to interpolate the coordinates exactly the same way we interpolate the displacement. So we are going to add some extra quality or add some extra quantity into the problem that we are going to interpolate also in using the shape functions. So far, we have been interpolating everything using the shape functions. We are been interpolating displacement, strains, stresses, but not the coordinate themselves. But now we are going to add one step into this, and this is going to be interpolating the coordinate as well. Obviously, we need to do something about the coordinates because the coordinates now are a completely different coordinate system. We are talking about xi. Okay, so this is one point I'm going to come back to after we do the shape functions. Now, we have the element. We are going to derive the shape functions. We will derive the shape functions exactly like we did before. So u is going to be a. Now, instead of x, we have xi plus b. So this is the displacement at xi equal to -1. We have u to be equal to u1. This is the first node. And this will be then, we are going to replace xi with -1, a -1 plus b. And at xi is equal to +1, we have u to be equal to u2. And this is a multiplied by 1 plus b. Now we have two equations with two unknowns. I'm going to write them down here. u1 equal to -a plus b, and u2 is equal to a plus b. So we have two equations with two unknowns. The unknowns are a and b. We are going to solve them. I just add them together, and this will cancel a. So you will have u1 added to u2 equal to a minus a is 0, equal to 2b. So this will give us B is U1 added to U2 divided by 2. So this is the value of the B. Now, instead of adding them together, I'm just going to multiply the first equation with -1 and add it again. So this way I can cancel the B. So if I multiply it with -1, this is going to be plus, and this is going to be minus. And then I have minus here as well. Okay, so I have now minus U1 added to U2, and then a B minus B is going to cancel. I will have 2A instead here. And this will give me, I'll just write it below. So this will give me A to be minus U1 plus U2. So it is U2 minus U1 divided by 2 is the value of A. Now I'll just insert these back into the original equation, which is this one here. So I put them back, this one and this one. I put them back in here, and then I will have U to be A is U2 minus U1 divided by 2 multiplied with xi added to U1 plus U2 divided by 2. All right, so this is the equation for U. The shape functions process, the way to find the shape function is exactly still the same like before. So I will have everything to be rearranged according to U1 and U2. So this is U1 and this is U1. So I will have minus U1 divided by 2 xi added to U1 divided by 2. And then I have U2 divided by 2 multiplied by xi added to U2. Okay, so I'm just going to take U1 and U2 as a common factor. So I will have U to be U1, and then I'm going to take the half as well. So this is half in there. Sorry, this is divided by 2 as well. So this is half in there and half in there. So everything is divided by 2. I'll just take the half as well as a common factor. And then I will have 1 minus xi added to U2 half 1 plus xi. All right, so this is xi and this is 1. All right, so this way I can simply write in matrix form half 1 minus xi and half 1 plus xi multiplied by U1 and U2. So this is basically the first equation we are going to find out. So this is the first equation. This is the equation in here. So this one I have been able to find. Now I'm going to do the same thing for the coordinates. So just simply, I'm going to write the same thing also for the coordinates. So I'll have x to be half 1 minus xi and half 1 plus xi multiplied by x1 and x2. Okay, so this is my second step also done. I just take it slightly further away. So this is my second step also done. And I have that. Now the tricky step. Now this is pretty much the new thing in the lecture today. And if you want, this is probably the point where you really want to concentrate if you want to understand the key points in this lecture today. Probably this is the most difficult one as well. And the challenging one. So you have the displacement to be the derivative of U. So you have the strain to be the derivative of the displacement with respect to x. Now, if you look into the displacement, you'll see that the displacements are now function of xi, not function of x. So this is a bit something we need to be careful about. However, there is some relation between x and xi. So the relation is this one. Okay, so we have a relation between x and xi, and we have a relation between u and xi. We want to find the relation between this whole thing so that we can find the strain as a derivative of the displacement. So I'm just going to write down the strains down here, and then we are going to see how to deal with them. So the strain is basically the derivative of u with respect to x. In the past, we have this to be the derivative of the first shape function with respect to x and the derivative of the second shape function with respect to x multiplied by u1 and u2. So this is how we had the strain in the past. Now we don't have the shape functions to be functions of x. However, we have the shape functions to be functions of xi. Okay, so what we are going to do now, we are going to use the chain rule. So the derivative of u with respect to xi, and then the derivative of xi with respect to x is the same like to find the derivative of u with respect to x. This is just the chain rule. Now finding this bit here is easy because I just replace x with xi in here. Now finding the derivative with respect, the derivative of x with respect, or the xi with respect to x is something I cannot find directly. Because I don't have xi to be a function of x, I have it the other way around. I have x to be a function of xi. So I cannot find the derivative of xi with respect to x, but I can find the derivative of x with respect to xi. So dx over dxi is something I can do, but I cannot do this one. So in this case, I will just find this one and inverse it. Okay, so I'm just going to find the derivative of x with respect to xi and inverse it, and then I will get the derivative of xi with respect to x, multiply that with the derivative of u with respect to xi, and get the strain. Okay, so I just need to find this guy here. The derivative of x with respect to xi is done exactly in the same way like I did the displacement. Oops, sorry. So this is the x, this is n1, and this is n2, and this is x1 and x2. So the derivative of x with respect to xi is just the derivative of n1 with respect to xi, the derivative of n2 with respect to xi, multiplied by x1 and x2. All right, so the derivative of f1, the derivative of n1 with respect to xi is simply minus half, half multiplied by 1 minus xi. So the derivative of this guy with respect to xi is just going to be minus half. This will go to 0 and this will go to 1. So this is going to be minus half. And if you look into the second one, this will go to 1 and this will go to 0. So I will have plus half. So the derivative here is simply minus half and half multiplied by x1 and x2. Now, what is x1 and what is x2? x1 is at the start of your beam and x2 at the end of your beam. So this is 0 and this is L. I'm just going to substitute them in here. So this is going to be 0 and L. So 0 multiplied with minus half will go to 0. L multiplied with half is going to be L over 2. So this is the derivative of x with respect to xi. I have that. So in order to get this one, I just inverse it. So inversing this is just simple. It's going to be just 2 over L. And then this this will go in here. So the strain now is going to be du over dxi multiplied by L by 2 over L. Okay, so once I have this expression, I can easily find the strain. So the strain in this case is just going to be the derivative of the shape functions. I've already found the derivative of the shape functions with respect to xi. So I'm just going to expand that. I'm just going to take 2 over L first, and then we have the derivative of N1 with respect to psi, the derivative of N2 with respect to psi, multiplied by U1 and U2. You remember that you had this thing here to be the B matrix in the past. Now we have one addition to the B matrix, so this is the whole thing. All right, so the B matrix in this case is 2 over L multiplied by dN1 with respect to psi, dN2 with respect to psi. I'm just going to write down the thing. So it is 2 over L multiplied by minus half and plus half. You remember that this is basically the same thing here. It is N1 with respect to psi is minus half and half. Again, I'll just show you the shape function so you remember them. This is 1 minus xi. The derivative is minus half, and 1 plus xi multiplied by half is the derivative is just 1 over 2 is half. And then I have the U1, U2. So I'm just going to do this one multiplied by this. So the 2 will cancel with the 2, and the L will remain at the bottom. And this is going to be minus 1 over L, 1 over L, multiplied by U1 and U2. Now, if you remember, this is exactly the same B matrix we had in the past. I mean, the original B matrix is minus 1 over L, 1 over L. And this is the scaling factor I've talked about. Okay. Now, this scaling factor is so obvious and so clear in the 2-noded element so that you can immediately see it. I mean, this is going between minus 1 to plus 1 in terms of xi, where xi is starting 0 here, whereas in the past we had the length to be running between x equal to 0 and x2 is equal to L, and the length is L. So this is basically the full length is 2, and this is the full length is L. So the scaling factor between the both is going to be L over 2. Right? So if you want to scale forwards and backward, you just use this scaling factor. Now, the exact same process would happen for higher order elements, but then for higher order elements, this scaling factor is not going to be obvious anymore. It's going to be completely random number for you. I mean, if you look at it, it's going to look like a random number, whereas in reality, it's just some sort of a scaling process. Now, the generalization of this process for any order of elements or for any dimension is called the Jacobian matrix. Now, this thing here, this guy here, is again very famous in math and is called the Jacobian matrix. And the Jacobian matrix would work, I mean, it has several applications in mathematics, and it has several applications in the finite element method as well. Now, the first application for the Jacobian matrix is to be able to transfer the B matrix between the coordinate systems, between local and the global coordinate system. You inverse the Jacobian matrix, you multiply it with the derivative of the shape functions in the local coordinate system, you have the B matrix in the global coordinate system. So this is the first application. Now, the second application we will come to when we need to find the integral. Now, you remember here, we have this step completed. And this step completed, we have the B matrix. If we have the B matrix and we have the strain, we immediately get the stress. The stress, this is just the elasticity modulus. Elasticity modulus has no meaning in local or global coordinates, has no difference meaning in local or global coordinates, is always going to be the same elasticity modulus. Now, if we get into a situation where the material properties would change within the element itself, then in this case, this would be different. But for the type of linear finite element, homogeneous finite element we have been working on in this course, this is always going to be constant, is going to be independent on the coordinate system. It has nothing to do with the coordinate system. Okay, so we have the strain We have the stress, we have the B matrix, we have the displacement, we have the coordinates. The one thing that is left for us is the stiffness matrix to do. Now, the stiffness matrix is the second tricky bit here because we have the stiffness matrix to be integrated with respect to x, not xi, and we don't have x anymore, we have xi. So how to be able to figure out what is the stiffness matrix? This is the second place where we need the Jacobian matrix. So in math, to transfer between coordinate system, you use the Jacobian matrix to do the transformation. As I said, in one dimension, in two noded elements, this is just a scaling process. Whereas if you get into three noded elements, if you get into a higher number of dimensions, the Jacobian matrix will be an obvious scaling factor. I mean, it works exactly the same way, but it's not going to be obvious. So to make the transformation, the stiffness matrix will need to be, I'm just going to rewrite it, integrate between -1 to +1, and we have the B transpose multiplied with D, which is simply the elasticity modulus multiplied with B, and then integrated over xi. Now, obviously, we cannot make this change unless we introduce something, and this something is the Jacobian matrix again. And it is not the Jacobian matrix, it's the determinants of the Jacobian matrix. Now, we have the Jacobian matrix to be L over 2. So the inverse of the Jacobian matrix is going to be 2 over L. Okay, so this is the Jacobian matrix. This is the Jacobian matrix here. It is 2 over L. This is the Jacobian. And the inverse of the Jacobian is what we used here. So this is the inverse of the Jacobian. So I'm introducing this new notation into the course, or into this course, but this notation is consistent with any finite element literature, or this is pretty much a mathematical notation. I mean, this is a very well-known notation. I mean, if you want, you can dig into the literature, or just Google the Jacobian matrix, and you will see what is the extent of the Jacobian matrix. I mean, you have a huge Wikipedia article on the Jacobian matrix. I mean, since I've mentioned it, probably I show you that as well. Yeah, so this is the full extent of the Jacobian matrix. I mean, it's quite some mathematical topic to look into if you are interested. Okay. So it is related to quite few. I mean, it's related to quite few applications in the literature, as I said. But for the finite element course, what we are limiting ourselves to is just the one-dimensional case. We are going to discuss it in 2 dimensions, but in 2 dimensions, it would be just a discussion. It's not going to get into the details of the math. So this is the Jacobian, 2 over L. The inverse of the Jacobian is L over 2. Sorry, this is the Jacobian, is L over 2. It's not this one here. And this is the inverse of the Jacobian. So I'll probably just write this as the inverse. And this is the Jacobian. Okay, so the L over 2 is the scaling factor I've talked about. And the inverse of that is 2 over L. You use the inverse of the Jacobian, you use the 2 over L to find the relation between the B matrix in the local and the B matrix in the global. Okay, so the other thing which just mentioned, the place where we need the Jacobian matrix is the stiffness matrix. I'll probably just write down, I'll probably just continue writing on the same page. I'll just copy the expression or just write it here. So the Jacobian matrix, the stiffness matrix is now A, E. I'm just taking the D matrix outside, integral between -1 to +1, B transpose multiplied by B, multiplied by the determinants of the Jacobian matrix and d xi. Now the G matrix or the Jacobian matrix is L over 2. The determinant of the Jacobian matrix is just the same. I mean, this is not a matrix, this is a scalar, so this is going to stay the same. So this will be replaced by L over 2. And then the B matrix, I have that. This is this guy here. So it is minus 1 over L, 1 over L. So just write down that. A, E, and then integral between minus 1 to plus 1. I have minus 1 over L, 1 over L, multiplied by minus 1 over L, 1 over L. So this is the multiplication multiplied by L over 2 and dxi. So if you look into the entries of this matrix, this is going to be 1 over L squared, 1 over L squared minus, 1 over L squared minus, and 1 over L squared. So I just take the L 1 over L squared as a common factor, is going to be A E over L squared, the integral minus 1 to plus 1 for 1 minus 1 minus 1 and 1. And L over 2, I'll just take it to the outside, so it is L over 2, so the L will cancel with the square. And then I have the integral over xi. So what you are left with is just EA over 2L. And the integral of these entries. Now, this is constant. I'll just take it outside the integral. I'm going to integrate dxi between minus 1 and 1. Just shift this slightly here. And then take this thing and put it here. This is constant. So you don't need to integrate every single entry, it is just a constant. So the integral of xi between minus 1 to plus 1 is just xi. So this is equal to A E to L, 1 minus 1 minus 1 and 1. And the integral here is going to be xi running between minus 1 and plus 1. So this is basically multiplied by 1 minus minus 1. Or this is going to be then, this is equal to 2, and 2 will go away with the 2, and you will be left with EA over L multiplied by plus 1, minus 1, minus 1, and plus 1. And this is your stiffness matrix, which is exactly the same stiffness matrix we have used in the past, but done on the local coordinates. All right. So as I said, the process itself does not make much sense in two-noded elements because it just looks like scaling things back and forth for absolutely no reason. But in the reality of it, I mean, once you get into more complex behavior, you will see what is the reason why we do this. And in fact, if I explain it on the three-noded element, not the two-noded element, where things would make much better sense, you would immediately get confused. So this is why I did it on the two-noded element. Now I'm going to do it one more time using the presentation. This is the original element we have running between x equal to 0 to x equal to L. This is the reference element we have is between minus 1 and plus 1. First thing we did the shape functions in the new coordinate system. So these are the shape functions in the new coordinate system. And then we need to find, I mean, the first challenge is to find the relation between the strain and the displacement. So the displacements are differentiated with respect to the global coordinates, the x. We need to find the derivative with respect to the xi. So this is why we use the chain rule. So this is just the chain rule. the derivative of u with respect to xi multiplied with the derivative of xi with respect to x. Now this guy is very famous. We call this guy the Jacobian matrix. And this guy is easy to find because this is just like du with respect to x. We have the shape functions in respect to xi, so this is easy to derive. This is just the derivative of the shape functions. It's minus half and half. Whereas this guy here, the Jacobian matrix here, we cannot find, but we can find the inverse of it. So it is dx over dxi. Okay, so this is minus half and half. Again, this is the B matrix multiplied with the x1, x2. So this is the Jacobian matrix, and then we need to find the inverse of that. So this is the Jacobian, this is the inverse of the Jacobian. I keep mixing up the Jacobian and its inverse. So this is the Jacobian matrix. This is the inverse of the Jacobian matrix. So you find the Jacobian matrix, you inverse it, and then you find the missing bit in the strain. So this is the Jacobian. This is the inverse of the Jacobian. You use the inverse of the Jacobian multiplied by the B matrix. So this is basically the new B matrix here. Okay, so this is the B matrix. You get the B matrix. You have the first piece that you need. The second place you need the Jacobian matrix is to shift the integral from x to xi. So basically what you are doing here, you are replacing these boundaries for your integral started from 0 to L. You replace them with 1 minus 1, and you replace dx with the Jacobian matrix determinants multiplied by dxi. So you move the entire integration from the global coordinate system to the local coordinate system by simply multiplying by the determinants of the Jacobian matrix. And then you just find the stiffness matrix the same way as before. The integral would happen the same way. There's only one element added. This is the determinants of the Jacobian, and the determinant of the Jacobian is L over 2. You have it in there, and you'll get back to the exactly same stiffness matrix we have in the past. Okay, so this is how it works. And now I want you to think about it a little bit just by using numbers. I mean, I've used L and E and A. I want you to do that. Find the Jacobian matrix just using numerical, just using numerics, all right? So I want you to basically read through the material we have been discussing today, basically the derivation. I'm going to give you 10 minutes. And as an exercise, think about it, try to digest this information and use numbers instead of symbols, okay? So basically the Jacobian is dx over dxi, and this is basically the derivative of the shape functions multiplied by x. All right, see, this is the Jacobian. I want you to figure out what is the exact number of the Jacobian in this example. As I said, I mean, this is just a numerical. This is just for you to encourage you to read through what we have done today before I move into the 3 noded elements. Okay, so I'm going to give you 10 minutes. Take 10 minutes to read what I've been showing you, and then try to find the value of the Jacobian. All right, so I'll just go through this example quickly. As I said, this is pretty much a repetition of what we have done so far. The Jacobian is the derivative of x with respect to xi. This is simply just the derivative of n1 with respect to xi and n2 with respect to xi multiplied by x1 and x2. if you do that, this derivative is going to be minus half, and this is half, and x1 is going to be 0, and x2 is going to be 5. So if you, so the length is 10, sorry. The length is 10, is not 5. This is going to be 10. And 0 multiplied by minus half is 0. 10 multiplied by half is 5. So the Jacobian is 5. You multiply that with the B matrix. So this is 1 over 5 multiplied by minus half and half. And by the way, the Jacobian matrix, also the B matrix is constant all the time. So you don't need to calculate the B matrix. You only need to calculate the Jacobian, and you multiply it with minus half and plus half in this case. Once you have that, you multiply the B matrix transposed by the B matrix, and you integrate over the range minus 1 to plus 1 over xi after multiplying again with the Jacobian. So the Jacobian is again 5 multiplied by these quantities. So this is what you get, the stiffness matrix. Okay, so now what I'm going to do, I'm going to repeat the process again for the 3-noded elements. And let us move into this one. Okay, again, this is the new element. This is the new coordinate system. And this is the original one. So this is the xi is running between minus 1, 0, and plus 1. The original element we had, it was x equal to 0, x equal to L over 2, x equal to L. So I'm just going to derive the stiffness matrix for this element here, but in this local coordinate system. So whenever, I'm going to derive the process for the xi, and then I'm going to implement it in this case, and I should get back the same stiffness matrix for this one, and then I will repeat it one more time for this element here, where x is equal to 0, x is equal to L over 4, and x equal to L. And then I'm going to get the stiffness matrix for this one as well. So I'm just going to derive the stiffness matrix for the original one, and then I'm going to implement it on this case and on this case. So this is the plan now. Okay, so just remove these from the screen for the time being. So that you don't get confused. Okay, first step is to derive the shape functions. U is a x squared plus b x plus c at, sorry, it's not x, it's xi now. X, or xi squared plus b xi plus c at xi equal to minus 1, so we're starting at the first node here. This is the second node, and this is the third node. So at xi equal to minus 1, we have u to be equal to u1 to be minus 1 squared, a minus 1 squared plus b minus 1 plus c. And then at xi equal to 0, we have u to be equal to u2, and this is a multiplied with 0 plus b multiplied with 0 plus c. And then finally at xi equal to plus 1, we have u to be equal to u3, and this is a multiplied with 1 squared, this is 0 squared, plus b multiplied by 1 plus c. Okay, so I'm just going to organize these equations, just rearrange them. If you look into this equation, this is going to 0 and this is going to 0. You are only left with c equal to u2. So I've got my first unknown, and I'm only left to find a and b. I'm just going to rewrite these equations in a neater way. So I first have u1 equal to minus a plus b plus c, and then u3 is equal to a plus b plus c. I already know c is equal to u2. I'm just going to replace it with u2 and take it to this end. So it's going to be minus u2, and this is minus u2 here, and I can cancel this guy. Okay, so I have two equations with two unknowns. The equations are relatively simple, should be easy to solve. Okay, so first I add the two equations together, we'll cancel the A, and I will be left with B. So I have U1 minus 2 U2 plus U3 is equal to 2B. And this will give me B to be U1 minus 2 U2 plus U3 divided by 2. And I have the value of B, sorry. Yeah, is better. And then I need to repeat the same thing, but multiplying the first equation with -1. Multiplying the first equation with -1, this will become minus, this will become plus, this will become minus, and this will become plus. Yeah, plus. So this is the one. Now add them together. So this should be, all right, okay. So this should be a plus and this should be minus. And if you add them together, then in this case, this is going to be 2A, and this would be A, the value of A. And then we are going to do this after multiplying the equation with -1. And then in this case, this will become plus, this will become minus, minus, yeah, minus, and this will become plus. All right, so just remove this guy from here as well. And add them together. Now you will have 2B. So this one added to this one is 2B. This one will cancel. And then U3, you have it in there, minus U1, and U2 minus U2 will go to 0. So what you are left with is minus U1 added to U3. And this will give us the value of B equal to U3 minus U1 divided by 2. And I have A, B, and C. So I have the three quantities I need into this equation. This is A, B, and C. I'm just going to replace them below. So I have U to be A. This is A. This is U1 minus 2 U2 plus U3 over 2 multiplied by xi squared added to U3 minus U1 divided by 2 multiplied by xi added to U2. So again, just rearrange the whole thing for U1, U2, and U3. U is equal, first I have everything to do with U1, so this is U1 and this is U1. I have U1 divided by 2 multiplied by xi squared, and then minus U1 divided by 2 multiplied by xi, and then I need to take everything to do with U2. So this is to do with U2, and this is to do with U2. So this will be then minus 2 u2 divided by 2 multiplied by xi squared added to u2. And then I have the last part. This is the u3 and the u3. So just writing them down is going to be plus u3 divided by 2 xi squared added to u3 divided by 2 multiplied by xi. All right, I'm just going to rearrange, clean this a little bit so the 2 will cancel with the 2. U is going to be u1, just take u1 as a common factor. I'm going to take the half also as a common factor because it's repeated here and here. So it is going to be half u1 multiplied by half multiplied by xi squared minus xi. This is xi and this is xi squared. And then added to u2 multiplied by, again, I don't have the half in there. I've canceled the half. So I have u2 multiplied by 1. This is 1. And then this is minus xi squared. And then I have u3 multiplied by half multiplied by xi squared added to xi. So this is going to be my first shape function. This is my second shape function. And this is the third shape function. Okay, so I'll go back to this set of equations. I just remove this sign so I can go through the steps one by one. Again. So the first expression I have for the displacement, so this is the displacement. I just have that here. So the expression I have for the displacement is now going to look like this. U is equal to, in matrix form, half xi squared minus xi, and then I have 1 minus xi squared, and then the third entry is half xi squared plus xi multiplied by u1, u2, and u3. I do exactly the same thing for the coordinates. I just copy that, it's the same. Okay, and this is the same for the displacement, x1, x2, and x3. And now I need to find the B matrix. If you go back, you see that I need to find the strain now. Yeah, so you need to find the strain now. So this is the derivative of u with respect to x. This is basically the B matrix. And the B matrix, as I said, I just write it here. So the B matrix is just the inverse of the Jacobian multiplied by n1 with respect to xi, n2 with respect to xi, and n3 with respect to xi. So first I need to find the derivative of these shape functions with respect to xi, and then I need to find the inverse of the Jacobian. I'm going to start with the first one, the derivative of the shape functions. So for the time being, let us assume that you still don't have the Jacobian. So the derivative of the first shape function is half multiplied by 2 xi minus 1. The second one is minus 2 xi. And the last one is again half 2 xi plus 1. Then I need to find the Jacobian in order to find its inverse. To find the Jacobian is just is equal to dx, also delta x with respect to psi. So the derivative of delta x with respect to psi, and the derivative of delta x with respect to psi is just the shape functions multiplied by x1, x2, and x3. Now I have the derivative of the shape functions, so this is the derivative of the shape functions. I did it for the B matrix. Now I also need to find the x1, x2, and x3. Okay, so for the derivatives, I'm just going to copy this guy here. And replace it here. Yeah, I need to make it slightly bigger. And then I need to find x1, x2, and x3. Now x1 and x2 and x3, I said I'm going to do it for two elements. For this one first. So this is x1 equal to 0, x2 is equal to L over 2, and x3 is equal to L. So I'm just going to replace these values in there. 0, L over 2, and L. If you multiply them together, you will be left with the Jacobian. This will go to 0. This will go to minus 2 psi multiplied by L over 2. And then the last part is plus L over 2 multiplied by 2 psi added to 1. I'm just going to expand that. So the 2 will cancel with the 2. It is minus psi L, and then L over 2 multiplied by 2 psi. So you will have L xi, and then L over 2 multiplied by 1. This is plus L over 2. So this will go away with this, and I will be left with the Jacobian to be L over 2. Now this is, because the node is in the center still, the scaling process would become, again, an obvious process. We are still talking about one-dimensional problems, so it's just a matter of shifting the length. However, when we are going to consider the second element, where the second node is in a different place, then in this case, the scaling process would change. Okay, so this is the Jacobian. I've got that. I can find the inverse of the Jacobian. So the inverse of the Jacobian is 2 over L. And I'm just going to insert this in here so I can find the B matrix. Okay. The B matrix is then going to be 2 over L multiplied by the derivative of the shape functions. I'll just copy them and put them here. Okay, so I've got the B matrix as well. Now I should be able to find the stiffness matrix, and this is the expression I have for the stiffness matrix. Just going to copy that there. I'll probably just write it down there. So the stiffness matrix is going to be A, E. I'll just take them out immediately. Between -1 to +1, I have the B transpose multiplied by the B, multiplied by the determinants of the Jacobian, and the integral is happening over xi. So I've got the B matrix. I just need to multiply it and find the integral. I'm again going to probably just paste it here. I don't want to rewrite the whole thing. So this is the B matrix. And the transpose of the B matrix is going to be half 2 psi minus 1, and then minus 2 psi, and then half 2 psi plus 1. So this is the result. And the determinants of the Jacobian, I've got the Jacobian here. So it is L over 2. I'll just write it down. So it is L over 2. The integral over xi. And I have EA to the outside. So this is running between minus 1 to plus 1. And I have EI to the outside. And I've got the stiffness matrix here. Yeah, I'm running out of space. So I can now do any entry if you want. So for example, this one multiplied by this one, you can get it here. Or I can do just this one multiplied by this one, you get it into this component here. So I'm just going to do this one because this one is easier. I mean, you get the point, is not any difference. So the integral of this one is minus 4 psi squared integrated between minus 1 to plus 1 multiplied by L over 2 d psi, and then on the outside you have A E. This is K2 2. So this is going to be then A E, and the integral of minus 4 psi squared is going to be minus 4 psi to the power 3 divided by 3. And obviously you have L over 2. I'm going to take all the constant to the outside and simplify them slightly. So the minus 4 doesn't have to be in the integral. And the L over 2 doesn't have to be in the integral. So this will go between minus 1 to plus 1, and the 4 will cancel with the 2. So this is basically going to be E A over L. I mean, this should have been 2 over L, not L over 2. So this is the inverse of the Jacobian. Okay, so if you do that, you will get 1 over 3 minus 1 over 3, and then you will get, probably just go back to the presentation. Yeah, so these are the shape functions, N1, N2, and N3. This is the Jacobian. And this is the B matrix. And this is the B matrix as well here. So you have the B matrix multiplied by the B matrix. I should have added this part as well. I forgot to add this part. And then you have the term I've computed is this one multiplied by this one and integrated between minus 1 to plus 1. Yeah, and this is the Jacobian. Yeah, in here I do the K11, but if you do K22, it's just going to be the same. Probably just, yeah. Do you want me to do the evaluation of the integral? I think it's probably just, yeah, just simple math. I don't think I need to do that. So if you do that, you will get 7 over 3 for the first entry. And if you do the second entry, which is 2 psi multiplied by negative 2 psi, you should be getting 16 for the integral. So it is 16 over 3. And then you get exactly the same stiffness matrix like before, which we had for this 3-noded element, where we have the second node located at L over 2. If you do this, for this case, this is 0, this is L over 4, and this is L. I'll probably just go back and show you the Jacobian matrix only for this case. Yeah, I mean, when I did this, I made a few mistakes. First, I should have been using the plus sign because it is minus multiplied by minus. And then for the B matrix, I have 2 over L. I should have added the 2 over L and the 2 over L here. Yeah, and this is L over 2. Yeah, and if you do that, you should have 4 L squared. And if you do the integral, you will be getting 16 EA over L multiplied by 16 over 3. Okay, so if you want to do the second element, which is here, you have x to be L over 4. The only change would be, I mean, this process would remain pretty much the same. It is not going to change. This whole thing would remain the same. The only change you need to introduce is this one. This will become L over 4. And this will reflect in some change in the Jacobian matrix. So you had L over 2 multiplied by 2 psi. In this case, you have L over 4. So we'll cancel, but you'll still have 2 in there. And then in this case, what is going to be left here will not cancel together. So I'm just going to rewrite the Jacobian, only the Jacobian. This change. Just write down scratch. So you have minus 2 psi multiplied by L over 4, minus 2 psi multiplied by L over 4. And then this will go away with this. You have minus psi L over 2, and then you have plus L over 2 psi. So this is going to be L psi, and then you have plus L over 2. See, it is L psi over 2 negative and L psi positive. So this will be positive psi L over 2 added to L over 2, or you just take L over 2 as a common factor, and you have 1 plus psi in there. Now, the Jacobian matrix is going to look like this. And you can start to see that this is not a scaling, not an obvious scaling process, just like we did in the past. So this is slightly different. Okay, so before it was L over 2 when you had the node at the center. If you shift the nodes, there will be some function of psi happening in there. Now, the good thing is you don't have to repeat the process entirely. You just need to insert the correct x into the x vector, but then the whole thing would remain the same. So the B matrix would remain the same. You only need to consider that the B matrix would need to be multiplied by the new Jacobian, or by the inverse of the Jacobian. So I'm just going to inverse the Jacobian and the inverse of the Jacobian is going to be 2 over L multiplied by 1 plus psi. So this is the inverse of the Jacobian now. And if you go to the stiffness matrix, this determinant of the Jacobian will also need to be replaced. So when you come here, it is not L over 2, it is L over 2, L over 2 multiplied by 1 added to psi, d psi. And this guy here will become 2 over L1 plus xi and 2 over L1 plus xi. Things will not cancel out anymore, and you have xi at the top and xi at the bottom. So I'm just going to write the first integral here. How it looks like is going to look like this. I'll probably just write it here. So this is the first entry, and this is the Jacobian matrix, and you need to multiply this together. So you multiply it together and multiply it with itself. I probably have to write it down here. It's just small space in the PowerPoint presentation, but I think you need to see that. It's 2 over L1 plus xi multiplied by half xi minus half, and you need to multiply this with itself. So it's multiplied again with 2 L1 plus xi multiplied by xi minus half, and this is multiplied by the determinant of the Jacobian, which is L over 2 multiplied by 1 plus xi, and this whole thing integrated over xi between -1 to +1. If you do that and you do the full, this is EA to the outside, and this is the first entry in the stiffness matrix for this element here. This is 0, x is L over 4, and x is equal to L. Now, you need to evaluate quite a complex integral. I mean, if you simplify this, you'll see that this is really a nasty integral to evaluate. So you need to evaluate the entire integral. You need to evaluate it analytically, which is a bit difficult to evaluate analytically. So the only way to deal with that is to use a numerical integration. Now, the good news is this process would only happen once. So you basically need to derive the shape functions on the local coordinate system once. You need to find an expression for the Jacobian. This expression for the Jacobian then will only need to have some input related to this coordinate, and then this is going to do the mapping process. So basically, I'm going to just quickly explain the process in 2D, but we are going to come back again to this process. So you have some local coordinate system, you have this triangular element, 3-noded, for example, and then you can have any triangle you wish, which can be anything really. You don't have to stick with the original one. You only need to have the coordinates, so it is x1, y1, x2, y2, and x3, and y3. You insert this into the Jacobian, and then the Jacobian will give you this one. I will give you the new stiffness matrix. So you do the stiffness matrix for this new element. So you have the expression for the stiffness matrix. You just need to insert the coordinate into the Jacobian. You get the stiffness matrix on the other side. This is basically how it works. So you have the expressions all happening in this local coordinates. In order to find the Jacobian, or in order to find the stiffness matrix, you need to find the Jacobian matrix. And in 2D, I mean, you can already start to see these changes once we increase the order from 2-noded to 3-noded. But once we move into 2 dimensions, this one here, this matrix is going to become a real matrix. It's not going to be a scalar. So it's going to be 2x2 matrix. And if we move into 3 coordinates, it's going to be 3x3 matrix. It's going to be a real matrix. So you need to find the Jacobian, insert it into this expression we have derived for this reference element. You give the stiffness matrix for this element here. And you repeat the same thing for all these elements. So you have the coordinates, x and y. You insert them into the Jacobian. You get the stiffness matrix for this new element, and so on for all of them. Okay, so I don't think this lecture today, I don't think it is an easy one, and I think it's a bit theoretical one, but this way, I mean, this is something I couldn't avoid, is just It's just the way it is. I've tried to simplify it as much as I can, but I think it is something that you need to work on your own time on in order to understand. Okay, and in order to understand that, you need to also understand the concept of the shape functions. You need to understand how we did the stiffness matrix for the global coordinates, and basically the whole process behind this mapping process. Okay, so this is why I said at the beginning, it is going to be some sort of a chain. You can't really avoid any link in this change. So it's in this chain. Okay, so to understand this, you should have understood things behind it as well. So I'm going to stop today. I think as I said, I think the lecture is a bit too lengthy from the theoretical point of view. I mean, we finished that in 2 hours, but usually it would, I wouldn't get into other material for the lecture of today.